Look up at the night sky, you see stars. Countless twinkling stars. Perhaps a planet or the moon, maybe even a distant galaxy, a faint smudge. This is the universe we know. The universe that shines. But what if I told you this is not most of it? What if the shining part is just a tiny fraction? The universe, it turns out, is mostly invisible. Most of what makes up the cosmos does not shine. It doesn't emit light. It doesn't reflect light. It doesn't absorb light in any way we easily detect. It's not made of the atoms that make you, or the atoms that make the Earth, or the stars. This invisible stuff is a profound mystery. It pervades everything, yet slips through our fingers. It shapes the universe, yet hides from our eyes. This mysterious unseen majority is called dark matter. It's dark because it doesn't interact with light. It's matter because it has mass. And that gravity is the key. Our story of dark matter begins in the 1930s. An astronomer named Fritz Zwicky was studying galaxies. Not just any galaxies. He was observing the Coma Cluster, a huge collection of galaxies, all bound by gravity. Zwicky was a brilliant if eccentric character. He looked at how fast these galaxies were moving, and he found something very, very strange. The universe was already throwing curveballs. Zwicky measured the speeds of individual galaxies. Within the Coma Cluster, they were zipping around. He used their light, their Doppler shift, to clock their speeds. He then estimated the total mass of the cluster. How? By counting the galaxies in their visible light. He assumed more light meant more mass. Then he calculated the gravity needed to hold the cluster together. The galaxies were moving too fast, way too fast for the amount of visible matter. The gravity from all the stars Zwicky could see, it simply wasn't enough. Zwicky knew something else must be there, something unseen providing extra gravitational glue. He called this missing mass Dunkelmaterie. That's German for dark matter. Zwicky's early observations were just the beginning. Decades later, another astronomer provided more compelling evidence. Her name was Vera Rubin. She was studying the rotation of individual galaxies, specifically spiral galaxies like our own Milky Way. She expected stars farther from the galactic center to move slower, just like outer planets in our solar system orbit the sun slower. But that's not what she found. Vera Rubin and her colleague Kent Ford looked at stars. They measured their speeds at different distances from the galaxy's center. What they discovered was astonishing. Stars on the outskirts of galaxies were moving just as fast as stars closer to the center. This defied Newtonian physics. If you only counted visible matter, there had to be more mass than we could see, a lot more mass, spread out in a vast halo. This halo extended far beyond the visible disk of stars. This unseen mass was, again, dark matter. Rubin's work in the 1970s was meticulous. Her data was undeniable. It provided strong, independent confirmation of Zwicky's idea. Galaxies weren't just flying apart in clusters. They were spinning themselves too fast. Something invisible was holding them together. This flat rotation curve became a hallmark of dark matter. Section 4, Cosmic Hide and Seek. What could dark matter be? So, we know dark matter is out there. Its gravity shapes the cosmos. But what it? That's the billion-dollar question. Maybe trillion. Physicists have many ideas, but no definitive answers yet. It's not ordinary matter that's just dim, not like faint stars or cold gas clouds. We've looked for those. They don't add up. The universe's composition, from Big Bang nucleosynthesis, tells us there simply isn't enough ordinary baryonic matter, so it must be something exotic, something new. One leading candidate is a type of particle, called WIMPs, weakly interacting massive particles. Weakly interacting means they rarely bump into ordinary matter, except through gravity, and possibly the weak nuclear force. This explains why they are so hard to detect. They would pass right through you, right through Earth. Millions, perhaps billions of WIMPs might be streaming through you now. Massive means they have significant mass, enough to provide the gravitational effects we observe. Many theories beyond the standard model of particle physics predict WIMPs. Another contender is the axion. Axions are hypothetical elementary particles. They are predicted by a theory that solves a problem in particle physics. Section 5. The universe's scaffolding. Dark matter's crucial role. Why should we care so much about this invisible stuff? Beyond pure curiosity, which is a good reason itself. Well, dark matter isn't just a cosmic oddity, it's fundamental to our existence. It's the architect of the universe as we know it. Without dark matter, galaxies might not have formed, at least not in the way they did, not with the structures we see today. And without galaxies, there would be no stars like our sun, no planets like Earth, and therefore no us. In the early universe, things were very smooth, almost perfectly uniform distribution of matter and energy, but there were tiny fluctuations, tiny density variations. These were the seeds of future structures. Ordinary matter, the stuff of atoms, interacts with light. This light pressure resisted clumping together too quickly. Dark matter, however, doesn't care about light. It only feels gravity. So it began to clump together much earlier, forming gravitational wells or halos. These dark matter halos acted as cosmic scaffolds. They provided the gravitational anchors. Section 6. Peering into the dark, the ongoing quest and future glimpses. The hunt for dark matter is one of the biggest efforts in modern science. Physicists and astronomers are attacking this problem from all angles. It's a global endeavor, pushing the boundaries of technology. We are trying to detect these elusive particles directly. Deep underground, shielded from cosmic rays. Experiments use ultra-sensitive detectors, waiting for a rare WIMP to bump into an atomic nucleus. Just a tiny little nudge. These experiments are incredibly challenging, like listening for a single pin drop in a hurricane. Other experiments search for dark matter indirectly. If dark matter particles like WIMPs can collide with each other, they might annihilate or decay, producing ordinary particles we can detect, like gamma rays, neutrinos, or antimatter particles. Telescopes search for these signals from regions rich in dark matter. Regions like the center of our Milky Way galaxy, or dwarf galaxies which are thought to be dominated by dark matter. So far, no unambiguous signal has been confirmed, but the search continues with ever-improving instruments. Particle accelerators like the Large Hadron Collider (LHC) at CERN, they also play a role. They smash particles together at incredible energies, trying to create new particles, perhaps even dark matter particles.